Hello everyone, today I will be kind of following a request. However, first of all, I've recently written a rather difficult test and now I've got a lot more time. I didn't have a lot of time to make videos within the last week. Now I have more time, so there will be more videos coming, maybe new formats. I also have more time to think about new formats to do and things like that. But now to the actual topic. 32,353,235 asked me to make a video about the RD-600 engine. Now, unfortunately, there's not really much about the RD-600 engine that to make a video about, so I'll make a video about also the RD-600 engine, but also the whole topic around it, that is nuclear propulsion, and I'll also talk about the RD-600 engine as it comes up within this topic. Now, in general, nuclear propulsion is the idea of using some sort of a nuclear energy source, be it an actual reactor or just an RTG, to produce energy and in whatever way use that energy to propel a vehicle. Most interestingly, a spacecraft. So nuclear rocket engines, though not only nuclear rocket engines, because the easiest and the only actually really seriously done way of nuclear space propulsion today is nuclear electric propulsion, which uses an RTG, a radioisotope generator, which isn't strictly speaking a nuclear reactor, but it uses a slow burning, stable, not really burning, a slowly decomposing nuclear fuel, and the heat generated by that is bled off via radiators, and in between that the temperature difference between the slowly decomposing nuclear fuel and the radiator is used to produce energy via Peltier elements, for example. And of course, you can use this electric energy to power an electric space propulsion system like an ion engine, or actually that's the most famous, but there are a few more electric space propulsion systems like arc jets, for example, but usually it's an ion engine. This is useful because, first of all, you have to get your energy from somewhere if you want to use electric space propulsion. And there's really only two effective ways, that's solar panels or RTG. And solar panels are only effective as long as you stay somewhere nearby the sun. So as soon as you want to go into the outer planets or towards Pluto, for example, with a space probe, and you want it to be able to fly several high delta V maneuvers and thus want to use an electric space propulsion system, this is probably the propulsion to go to. Also, you'll probably need an RTG for onboard computer power if you go far away from the sun, so solar panels don't really work anymore. Actually, it's not just that solar panels produce less energy if you go far away from the sun. At some level of light intensity, they actually stop working altogether, although it is possible to design them to get energy at a somewhat low level of light intensity. There is actually a strict limit, and for example, the Rosetta probe that went to Comet C63P actually is the farthest away from the sun electric system that was ever powered by solar panels at all, and anywhere farther away from than that would just stop working altogether. Then you have the standard electric drive ion engine, electric field propelling ions, and basically you just sustain the energy via an RTG. Of course, there's also direct nuclear propulsion, which there are several concepts for. and the higher the specific impulse gets, the less safe and the less practical the concepts get. The most realistic version, which has actually been tested on the ground in both American and Russian test programs, is the solid core nuclear rocket engine, or nuclear thermal rocket engine, which essentially it works similar to a normal rocket engine, as you have a combustion chamber. There's no real combustion there, though it can be combined with a combustion, but you have a chamber, fuel or propellant is heated up in that chamber, it goes out through a nozzle and accelerates. Just instead of using a chemical reaction to heat it up, you use a nuclear reactor core that is suspended within or nearby the reaction chamber and the combustion chamber, and connected so that heat can easily flow. This is, of course, limited in specific impulse, because the specific impulse given a certain propellant, best being hydrogen, but really hard to transport too, so but given a certain propellant, and there's not much of a range of what kinds of propellants you can use, so there's a limited specific impulse for a given temperature, and there is just a limited temperature that a solid core can have, and a limited temperature that a reliable structure can sustain, and therefore the specific impulse of these is way below the theoretically energetically possible for a nuclear rocket engine, but therefore they are reliable and realistic to build. They get up to about 800 seconds of specific impulse, and those include the Russian RD-600 experimental engine, which was tested on the ground but never actually flown, as well as the American Nerva test engine, which is much easier to get more information on and pictures of, so that's what I'm showing here right now, which was test-fired in nuclear weapons testing grounds, but also never actually flown in space, and is a rather obvious inspiration for the Nerve engine in Kerbal Space Program, by the way. If you want to go higher specific impulse, there is the gas core or liquid core in between, or gas core nuclear thermal rocket engine, which essentially does away with the structure. So you have the little problem that you essentially throw bits of uranium or nuclear fuel into the exhaust stream, and pretty much anywhere you fly this will be nuclearly contaminated afterwards. But for deep space, they are kind of a hypothetical possibility. You wouldn't want to launch with that type of engine from Earth, but you can use them to fly through deep space. They have a way higher thrust-weight ratio than any electric system or any or the other nuclear thermal rocket engines, though still not quite as good as that of chemical rocket engines, but they have a really high specific impulse, theoretically ranging up way above 5,000 seconds or 50,000 meters per second. That is easily enough to basically cruise around through the solar system, not really caring much for orbital mechanics, because you're going to reach such high speeds that the gravity of the sun or other celestial bodies you encounter doesn't really deviate your course a lot. You'll have to do small course correction, but you'll pretty much be flying in an almost straight line from one celestial body to another. It's also probably closest, which is also kind of what I want to answer here, closest to what you might have in the iconic Tintin. I have no idea how to pronounce the English or French name, I only know those in German. The Tintin comic rocket, which isn't exactly realistic in all ways, but if you want to suspend your disbelief and hypothesize what it might be. It's probably a gas core nuclear thermal rocket. It's a quite iconic comic, and it's often mentioned in the spaceflight nerd or Kerbal Space Program scene, so I thought I'd mention that here. They also mention in the comic that they have to switch between engines because they don't want to irradiate their landing grounds. They don't want to contaminate the launch facility on Earth or their landing place on the Moon, so they actually use normal rocket engine for takeoff and landing, and just use the nuclear engine once they leave the Earth's atmosphere to go to the Moon until landing, and to go the whole distance in space. They don't actually use it for takeoff and landing. That's kind of what you would do with a real gas core nuclear thermal engine. So that's probably what they were using, but in reality this is still a kind of hypothetical concept. There's never really been a valid test model of these, only theoretical calculations and schematics. And if you want to go even more insane, if you want to say, there's of course the nuclear pulse propulsion, which is famously known as the NASA Orion program, not the new space capsule, but the name-sharing program from early spaceflight age, 60s, 70s. There were hypothetical concepts for deep space propulsion where you would have essentially nuclear bombs, which is pretty good because these can easily be scaled up to hydrogen bombs. It's of course difficult, but it's relatively easy to building a fusion reactor. So you could just scale this up to fusion propulsion. But the concept was essentially to throw nuclear bombs out the back of the spacecraft, detonate them, and the spacecraft would be pushed forward on the shockwave. Extremely high specific impulse, but extremely difficult to build. You would have a sort of pusher plate that is basically heavily armored, and it would be suspended behind the spacecraft with springs and dampeners so that the short impacts would be converted into sustained, still a kind of varying but no longer shock impacts, but a sort of varying but sustained propulsion. You would need small and really relatively small nuclear bombs compared to anything built on Earth, because you really want to go for the smallest nuclear bomb that is physically possible to build and detonate. But then it's theoretically possible, and there were test models, not really of this concept, but test models for a similar mechanism that were flown on Earth using regular explosives. They were really small scale models. So at least we've figured out that a pusher plate and a spring and dampeners suspension can actually transform a series of explosions into a varying but somewhat sustained and survivable level of thrust. There is actually test footage of this easily available on YouTube. Those were the most common or most discussed types of nuclear propulsion. There is still the aircraft version of the solid core rocket, which is essentially a turbofan or turbojet, where the combustion chamber is converted into just a heating chamber. There's no combustion going on there. The air just streams in, and there's a nuclear reactor actually a bit of a distance, a few meters away from the actual turbojet engine. and there's some sort of heat pipe or copper structure that transfers the heat into the no longer combustion chamber, but what would be the combustion chamber in a normal turbojet engine. That heats up the air, and the rest of the functioning is equivalent to a normal turbojet or turbofan engine. And aside from a few really exotic drives like nuclear fission sailing, these are the more commonly discussed theoretical systems for nuclear space propulsion. I hope this was kind of interesting, and I'm always open for requests, and thanks for watching.